Hello, today we're continuing in our series of GCSE physics revision, looking at electric circuits and in particular circuits in parallel. Last time we considered components that were in series. This time we're going to look at components that are in parallel, and what that means is we've got a battery, we've got a resistance, maybe R1, but in parallel with that we've got another resistance, R2, and in parallel with that we've got yet another resistance, R3. And those are each in parallel. And you'll notice that the voltage, which is the voltage of the battery, is wholly applied across each one of them. If you look, the line comes down, the voltage across that one is V. The voltage across that one is V. The voltage across that one is V. The whole voltage is across all the components. But the current is split. You've got a current coming down here, but when it gets here, some of it will go off down here, some of it will go off down here, and some of it will go off down there, and then it'll all reconnect and become the full current again here. So if we call this I1, I2 and I3, then the total current which flows from the battery will equal the sum of the currents going through each arm, I1 plus I2 plus I3. The total effective resistance of all these resistors, remember in series you would just add them up, but in parallel it's not that easy. In parallel, 1 over R, where R is the total effective resistance of all three of these, is given by 1 over R1 plus 1 over R2 plus 1 over R3. So if you want to find the total effective resistance, this time you've got to do a little bit more work. So let's suppose that R1 is 6 ohms, R2 is 4 ohms, and R3 is 3 ohms. What's the total resistance? Well, the total resistance is given by 1 over R equals 1 over R1, which is 1 over 6, plus 1 over R2, which is 1 over 4, plus 1 over R3, which is plus 1 over 3. And now you've got to know what your lowest common denominator is, and in this case it's going to be 12. 1 over 6 is the same as 2 over 12, plus 1 over 4 is the same as 3 over 12, plus 1 over 3 is the same as 4 over 12, and that gives you 2 plus 3 is 5, plus 4 is 9, 9 over 12. But don't think that that is the total resistance. That is 1 over the total resistance. So we have to turn both sides upside down to get that the total resistance is equal to 12 over 9. You have to tip this upside down to get the actual resistance, because this is 1 over R, so R is 12 over 9, which is 1.34, actually 1.33 recurring, isn't it, ohms. So now we can work out what the total current is, the current from the battery before it splits up. The total current we can work out from Ohm's law again. V equals IR, so consequently I equals V over R. Let's suppose that the battery, which I didn't tell you, let's say that's a 12 volt battery. So the current is going to be the battery voltage, which is 12, divided by the resistance, which we just calculated, 1.33. 12 divided by 1.33 is 9 amps. So the total current flowing from the battery is 9 amps. But what is the current flowing through each limb? Well, again, it's Ohm's law, V equals IR. In this case, V is always 12 because the total battery is across each of the resistors. So V is always 12. R, of course, is the actual values of the resistance. So let's take the first resistance, R1, whose value is 6 ohms. So if V equals IR, that means that I is equal to V over R, which in this case is 12 because the voltage is across all of those resistors each, but the resistor was 6 ohms. So it's 12 divided by 6, that's 2 amps. So 2 amps flows through the first resistor. What flows through the second resistor, which remember was a 4 ohm resistor? Well, here I is going to be V over R, which is 12 divided by 4, and that's going to be 3 amps. So through the second resistor, the 4 ohm resistor, you're going to get 3 amps. What about the third resistor, which is the 3 ohm resistor? Once again, 12 volts is across it, so that's V divided by R is 12 divided by 3 is 4 amps. So 4 amps will flow through the third resistor. So we've got 2, 3 and 4. So what that means is that 2 amps flows through this resistor, 3 amps flows through this resistor, 4 amps flows through this resistor, and if you notice, 2 plus 3 plus 4 is 9, and that's the total number of amps that are coming out of the battery. And if you want to do boot and braces, you can now prove that the voltage across each resistor, or the potential drop across each resistor, is indeed 12 volts, because the potential drop across each resistor will simply be the current through the resistor multiplied by the value of the resistor. So it's I1R1 in this case, it's I2R2 in this case, and it's I3R3 in this case. Let's just check to make sure that they all come to 12 volts, which is what I have claimed, because I'm saying that voltage is applying across each of them. So let's have a look what we just calculated. I1 we calculated was 2 amps. 2 amps was going through a 6 ohm resistor, so the voltage through the first resistor is equal to IR, which is equal to 2 amps, because that's what we calculated. It was a 6 ohm resistor, 2 times 6 is 12 volts. In the case of the second resistor, that was 3 amps times, and it was a 4 ohm resistor, 3 4s are 12 volts. In the third case, we've got a current of 4 times a resistance of 3, 12 volts. So whichever way you do it, you get that when things are in parallel, the whole voltage is across each component. Why might it be an advantage to wire things in parallel? Well, here's the battery, here is component 1, here is component 2 in parallel, here is component 3 in parallel, and you'll notice now that if it just so happens that this component, suppose it's a filament lamp, could be, suppose that completely breaks. No current flows in this part of the circuit because that limb has been broken because the component is broken. But there's nothing to stop it flowing in this or this part. So when one item fails when you're in parallel, it doesn't mess up everything else. Unlike, remember, the Christmas tree lights in series, if one of them goes, they all go. In parallel, one of them goes, the rest stay on.